this discussion we're going to get into a particular bandpass filter structure. In probably previous discussions we've probably talked about second order sections. We've also talked about various structures in terms of doing low pass filters. In this case we're actually going to talk about a bandpass filter, and there's a number of different topologies. But I want to talk about a topology that's at least close to my heart and things that we've used a bit, called a capacitively coupled current conveyor. Certainly often shortened as called a C4 structure. Now you might wonder, okay, where did this come from? And it actually started from some aspects in floating gate circuits and trying to actually model what actually happened in some of those circuits for some some of the basic adaptation mechanisms you might see. But the sort of typical circuit as it's typically used today, you might imagine two OTAs, particularly if this is done in an FPA structure. It has a very interesting thing for a GMC filter because it's one of the few that you would find that would, as far as I know, the first one that actually used as a bandpass used a capacitor as the input. And it's nice because it's a capacitive input, two OTAs, and so it actually tends to be lower noise than other topologies because certainly the capacitance itself is not an issue. There can of course be additional capacitance here, CW, down to ground or fixed potential. There can also be a capacitance from between the middle node, which was kind of analogous to the floating gate node in some of those circuits, to the output voltage. And that also would typically be C2. And trying to keep this consistent with some of the other discussions, there are much longer papers that go through this in great detail. But to kind of give a sense of what's possible, I kind of wanted to walk through a few of these aspects. Now, what's nice in the structures, you're going to be typically talking about having this set to two, having a signal ground here. This would probably typically could set your reference voltage for your structure. We're going to have two transconductance that are set, whether this is above or subthreshold. Certainly in subthreshold, these are pretty well understood structures, understood variables. The OTAs themselves could also have floating gates as the inputs or other sorts of means to have a wide linear range. And so often we'll want to talk about the transconductance in somewhat more general terms depending on the particular family and types of circuits you're working with. Now we'll typically see one of the typical ways to look at this is to look at this as sort of separated corners, where you have really wide spacing, got a very nice good band region. Typically this band region will be then a question of what was the gain in terms of the capacitor. This was a particular structure where the gain was set to be pretty close to 1, a little less than 1. And so you get a very nice response that looks like 20 dB per decade on this side, rolls into a corner, have multiple orders of magnitude for your passband, and then it rolls off on the other side. So you actually do get a nice high pass response and a almost separated low pass response. You do get a zero further down that you would eventually see that does not show up in this particular frequency plot. That's your tau sub h. You're going to look at three corners in a separated case: tau h, tau l, and tau high, tau low, and then sort of the tau that occurs towards the zero. The low corner is not surprising. It's really dependent on this sort of feedback transconductance element and the capacitance between V and V out. So a fairly reasonable sort of structure. Tau sub h takes a little more to calculate, but on the other hand, still very straightforward. It's entirely dependent on G sub GM4, but it has this complex term of CT, which is the total capacitance at this node, times the total capacitance C0 at this node, minus that value squared over C. That may seem like it's a fairly complex structure, but it turns out to be very useful. In a sense, it gives you sort of a multiplication of capacitance. It does, in one sense, look like a capacitor multiplier structure. And as a result, you can actually utilize this structure, say, particularly if I'm using C1 as sensor elements, I can utilize all the capacitors to some advantage. Now, if these OTAs are reasonably ideal OTAs, then you really only have two poles in the structure. So you actually are, or two state variables, one pole, one zero, one sort of pole zero, that come out of the structure. As a result, this is kind of where you begin to start talking about what's possible with this. And what's nice is if I have separated corners, if I have such a structure, I can move by simply changing the bias current of GM1, I can move this back and forth. The same thing is true, I can move for the high corner back and forth by changing GM4, and they're fairly independent. In fact, if I look at the step response for very slow sort of things, I can do a step response where it looks like a low pass just because I'm doing the steps fast enough compared to the corners. So what I've done here is I made the corners very slow, and so as a result it looks like it's just a low pass. And so there's a lot of different ways that if you're not sure of where your corners, you can get confused here. The more likely case for this case is looking for a high pass, as it drops immediately, jumps because of the initial input voltage due to the gain of the structure, and then returns back to equilibrium. So this would be very much consistent. The typical plot I would expect with either separate corners. This works depending on the speed at which I build it. I just kind of want to show what some of these structures look like. Now what's interesting is if I get these two corners, I can move them. And what happens if I move them together, I can actually get something that now looks like a bandpass structure. And so I can actually get, and these are again also experimental data, just like above, which is now talking about a bandpass structure. And I actually did 3 different ones, slightly moved it in each of these cases. And you can actually find that it actually is a pretty good bandpass with a reasonable resonance that it responds out of each of these. The math gets a little more complex, but still fairly reasonable all the way through. And there's a whole set of conversations in terms of what is the distortion and noise and other aspects, which are all fairly well modeled out, but just wanted to kind of show that you can do a reasonably good bandpass filter structure out of this as you would want. And if you look at the step response for it, you would actually see something that has a ringing response, returns back to equilibrium. And the same thing in the reverse, step in the other direction, reverse in the equilibrium. This is one of the more interesting structures to work with, and it's a very dense, very effective bandpass filter element. It has only 2 AGM elements. It tends to be fairly low noise compared to other approaches that you might build out of this. And again, every circuit designer has their preference, but this is the structure then that is used for many other classifier structures that you may look at, particularly acoustic front ends and other kinds of signal sort of sensor front ends in these structures. So from here you can build a tremendous number of other computations and other blocks, and it's small enough that building 10 or 20 of these on a particular process is particular computation is pretty easy to do.